in the Southern Ocean, I don't have a lot of data. This is a paper from Sarah Gill, who was at UCI a few years ago, and now is at Scripps, where she showed that there's some indication of warming in yellow here of the Southern Ocean, but of course it doesn't go all the way to the periphery of the Antarctic, so we don't really know what's happening here. This is in white because there's no data. But the ocean is probably warming too. And it's not so surprising that things are changing in the Antarctic. It's part of the global system. I think there was this maybe somehow naive preconcept that the whole globe could warm and Antarctica would just sit there and do nothing. The consequences for the Antarctic, well, it's still too cold to melt. Remember, you have to warm up the climate by 5 degrees to start melting Antarctica. We're going to get there, but it's going to take a little while. The more surprising result is that there's no accumulation trend. This is results from a US team, from Andrew Mulligan and et al. From Ohio State. Not much of a trend in accumulation in the Antarctic in the past 50 years. This is work from the Dutch. Same thing, the red bars here show the change in the last 25 years in precipitation in the Antarctic, not much of a trend. Snowfall changes every year in the Antarctic, but if you look at the last 50 years, it doesn't look like it's increasing or decreasing. Ice-ocean interaction. Well, let's not forget about that. I have a little cartoon here, which shows exactly what's happening. This is the floating extension of a glacier. The glacier is coming from the left here and is flowing into the ocean, and it developed into this ice shelf. The scale is really not representative. This part here is very flat and thin. The slopes of this, the basal slope of these ice shelves is measured in percent or fraction of a percent. But anyway, you have a sea ice formation that creates this denser saline water that can flow down the continental ice shelf, and the bedrock underneath Antarctica is slanted like this because the ice sheet is depressing the crust, right? It's sitting on the crust, so it's getting deeper inland. And this water is able to melt the ice, and meltwater rises because it's less dense and eventually reaches some equilibrium and flows out. You can have also a direct inflow of warm water from the outer ocean that melts the ice. Or you can have some coastal currents that affect the ice sheet. This process is very efficient. One of the reasons is that the melting point of ice decreases with pressure. And typically here you are 2 kilometers below the surface. And 2 kilometers below the surface, the melting point of ice is depressed by 1.5 degrees. So with the same water temperature, you can suddenly melt the ice a lot easier. And typical thermal forcing we have in the Antarctic is 1 to 4 degrees. Now there's something similar on the glaciers that terminate in the water. It's not been studied as well. In this case, you have this inflow of water here coming here and melting the ice and rising because you create meltwater that's less dense, and it creates this overflow plume that flows out. And this is fed by the subglacial discharge from the glacier. All the melting upstream from the ice is reaching the bed and comes out underneath right here as a very strong flow that helps this convective flow driven by water discharge. And thermal forcing here is higher because these glaciers typically sit in warmer climate. And because these faces are vertical, they also enhance this pattern because the meltwater flow can raise more quickly. It's not raising along a nearly flat ice shelf. It's raising along a vertical face.